Welcome to The Explainer. I am super excited you're joining us today because we've got a seriously fascinating topic to unpack. We're diving deep into the cutting-edge AI news surrounding graph neural networks, or GNNs, specifically focusing on link prediction. Today, we're pulling insights from a highly anticipated new archive survey that completely maps out the taxonomy of these architectures, alongside a groundbreaking paper from Nature Biomedical Engineering that takes this exact tech and applies it to biological knowledge graphs. So if you want to understand how AI connects the dots in everything from massive recommendation systems to discovering life-saving medicines, you are absolutely in the right place. Let's get into it. So think about this for a second. How exactly does an AI look at a vast, totally chaotic web of data and accurately guess the missing connections? We aren't just talking about it recommending a new friend on a social act, right? We're talking about mapping out molecular interactions to discover entirely new uses for existing drugs. It honestly feels a bit like magic, but it's actually highly structured, incredibly complex mathematics. And today, we're going to break down exactly how these models pull off these massive breakthroughs.
Okay, let's dive right into our map for today's explainer. We'll start with decoding link prediction, then move to the 4 core GNN architectures, navigating architectural trade-offs, powering deep knowledge graphs, scaling recommendation systems, and finally, future graph challenges.
Part 1, decoding link prediction. So what does this actually mean? Well, at its core, link prediction boils down to mathematically scoring potential edges between nodes. Imagine a graph where the nodes are entities, people, proteins, or products. Link prediction is the engine that infers the missing connections, or the edges, between them. If you've ever had a streaming service accurately suggest a new movie you end up loving, or, let's be real, completely miss the mark, you're looking at link prediction in action. It's all about calculating the probability that a specific, unseen relationship exists out there in the data. Moving on to Part 2, the 4 core GNN architectures. Now, what's really interesting here is the taxonomy outlined in the recent survey. We have 4 primary encoder families. First up are GCN-based models, which use spectral convolution, which is essentially a way of mathematically blending features from neighboring nodes. Next, we have GAE-based graph autoencoders. These learn by trying to reconstruct the entire network structure from a compressed latent space. Then, gap-based architectures use attention to dynamically weigh the importance of different neighbors. And finally, GFormer-based models bring transformer-style self-attention into the mix to capture long-range, multi-hop dependencies across the graph. Basically, each of these mechanisms acts as a different kind of lens for the AI to view the graph. All right, Part 3, navigating architectural trade-offs. Let's pit 2 heavyweights against each other, because choosing the right model depends entirely on your graph's specific topology. On one side, GCNs. They're fantastic because they're highly computationally stable. But there's a catch. If you build them too deep, they suffer from something called oversmoothing. That's where all the nodes start looking mathematically identical, which completely flattens any meaningful distinctions. On the other side, GATs solve this uniform aggregation problem perfectly by using attention. They offer incredible precision, especially on graphs where some nodes have massive amounts of connections, while others have practically none. But that precision, it has a cost. The attention matrix grows with the node count, which causes heavy inference latency. So you're essentially trading speed for precision. Section 4, powering deep knowledge graphs. This brings us from the theory into real-world territory. Enter a truly remarkable framework from Nature Biomedical Engineering called BioPathNet. It tackles incredibly complex biological knowledge graphs, but it doesn't just embed nodes into a vector space like traditional methods. Instead, built on the neural Bellman-Ford network, BioPathNet utilizes path-based reasoning. It learns the representations between a pair of nodes by considering all the different relationship paths that connect them across the graph. It's looking at the entire journey, you see, not just the destination. And the way BioPathNet manages the noise and sheer scale of biological data is brilliant. First, it integrates a background regulatory graph, or BRG. This enriches the connections during message passing without totally overloading the training process. Second, it applies node-type-aware negative sampling. So when training the AI on what a false connection looks like, it strictly uses negative examples that biologically make sense. By doing this, it accurately predicts multi-hop paths, which leads us to our next major point. The impact here is absolutely huge. BioPathNet used this exact path-based reasoning to identify promising real-world treatments for acute lymphoblastic leukemia and Alzheimer's disease. By optimizing how messages are passed and strictly controlling that negative sampling, they literally took abstract graph math and brought it to life with real, life-saving stakes. It's a stunning example of why optimizing link prediction matters so much in the real world. Part 5. Scaling recommendation systems. Now, shifting gears to the e-commerce and streaming world, user-item interactions are framed as bipartite graphs. That basically means you have two sets of nodes, users on one side, items on the other. Here, link prediction translates directly into collaborative filtering at a massive scale. GNNs propagate signals through co-rating neighborhoods, and when you run into a cold start problem, like say a brand new user with zero watch history, architectures like GAT and GFormer are leveraged to mitigate the sparsity of those interaction graphs. But here's the catch. The crucial bottleneck for all of this is latency, specifically hitting a sub-10 millisecond limit for per-user inference in production systems. I mean, you might have the most precise GFormer model in the world, but if it takes too long to calculate the attention matrix, the user's already scrolled away, right? Making these heavy, complex GNN models fit within a sub-10 millisecond window is a massive, ongoing engineering challenge.
Finally, Section 6. Future graph challenges. The industry is currently wrestling with three main roadblocks. First, dynamic graph handling. Real-world networks are constantly evolving, yet we kind of lack solid temporal benchmarks to measure how models adapt over time. Second, evaluation fragmentation. Depending on the framework you use, link prediction metrics are calculated differently, which makes it super hard to compare models fairly. And third, memory-bound inference. Those incredibly powerful GFormer and deep GAT models hit severe VRAM limits on standard GPUs very quickly. They literally turn your hardware into an expensive space heater. Sparse attention and unified evaluation pipelines are definitely becoming critical areas of research here.
Okay, so if you're a developer watching this, here is some actionable advice. To optimize your memory footprint, you absolutely must audit your adjacency matrix representations. Avoid those intuitive but heavy, dense matrices on sparse graphs. Use sparse CO or CSR formats instead, which compress the empty space to save massive amounts of memory. Also, make sure you're pinning your GNN library versions to maintain consistency. And hey, if you're taking the leap into GFormers, you need to implement blockwise attention early in the development cycle. That is crucial to ensure you can actually meet your service level agreements for inference speed. I want to leave you with this provocative question to ponder. Are you treating link prediction in your pipelines as a simple classification problem or as true graph completion? The survey highly recommends a shift in perspective here. By prioritizing ranking optimization over simple threshold tuning, you align much closer to how downstream retrieval systems actually work in practice. It's not just about a yes or no classification. It's about understanding the complete structure of your data. Thank you so much for joining me on this explainer today, and I really hope you leave with a much clearer picture of the incredible power of graph neural networks.